Hello dear students, welcome back to my class. It's my third lecture on ray optics and optical instruments. Today we'll be discussing the continuation from the previous class, that is the mirror equation. So let's start the class. So already we have derived the mirror equation, that is 1 by u plus 1 by v equal to 1 by f. Is it clear? And we have derived the expression for magnification, that is, this is linear magnification minus v by u. And as I have already told you, if the value of m is negative, the image is real, and real image is always inverted, and if the value of m is positive, that real must be virtual image, and virtual image is always erect. Okay. So today we'll continue from this part. Okay, now we'll try to express this expression of magnification in terms of object distance and focal length, and in terms of image distance and focal length. So first, magnification. So I'll write in short, this is m in terms of u means object distance and f means focal length. Okay. So from mirror equation. Okay. So what is mirror equation? That is 1 by v plus 1 by u plus 1 by v equal to 1 by f. So 1 by u plus 1 by v equal to 1 by f. Okay. So to express the magnification in terms of u and f, you have to remember one technique. Once you have to express this in terms of u and v, you just multiply the mirror equation on both sides by u. Okay, so you can write multiplying on both sides by u. So that is u into 1 by u, and u into 1 by v, and u into 1 by f. As you can see, like term, so we can cancel out. So this is 1 plus v by u, this is u by v. I hope it's clear. It's a simple mathematical calculation. So now I'll transfer this u by v term to the other side. So this is plus, so it becomes minus. So I'm writing 1 minus u by v, and I'll transfer this u by v term to the other side. So this is plus, so it will become minus. Is it clear? Okay. Now let's take LCM in the left hand side. So LCM is f, so we can write f minus u equal minus u by v. Okay, but what is the expression of magnification? It's v by u, but we have u by v. So what we'll do, we'll inverse the whole expression. So now denominator becomes numerator, and numerator will become denominator. So minus here also v by u. Now this minus v by u is nothing but m. So I can write f minus u equal to m. So this is the expression for linear magnification in terms of object distance and focal length. I hope it's clear. Okay, now we'll try to express the same expression, means the magnification in terms of image distance and object distance. Okay. Okay, you note down, you pause the video and note down. Okay, next, come to the next topic. This is magnification in terms of, this is v. V means image distance and focal length. Okay, so we'll start with the same, okay, same technique from the mirror equation. The mirror equation 1 by u plus 1 by v equal to 1 by f. So again we have to express in terms of v and u, so we'll multiply on both sides by v. So v into 1 by u, v into 1 by v, v into 1 by f. If you want to write this, you can write multiplying on both sides by v. Okay. Now this v and v will cancel out because they are like terms. Okay, now here you can write v by u. Now this is 1 v by f. So V by U, I'll transfer this 1 to the other side. 1 is plus. Once we transfer this plus 1 to the right hand side, it will become minus. So this is minus 1. So let's take LCM. So F, so V minus F. So V U. Okay. But the expression is minus V by U. So what we can do? We can multiply on both sides by minus. So here I'll write. So this is, once I multiply on both sides by minus, so it will become minus, or you can do one thing, you can transfer to the other side. So this is minus V by U, and then this is plus, so it will become minus. So this is minus, and this is F. So this minus V by U is nothing but M. So if I multiply this, minus plus minus and minus minus plus. So I'll write this F first because this is plus, and minus V and divided by F. So this is the expression of linear magnification in terms of image distance and focal length. So this is about the mirror equation and expression for the linear magnification. Now our reflection part is finished. Now we'll switch to the refraction part. Okay, but there are so many numericals we can solve by applying this mirror equation, and linear magnification numerical is very important. 9.1 and 9.2 you have to solve by yourself because the numerical is easy, just like you got in your class 10. Okay, now let's discuss what is refraction of the light. Okay, dear students, as you know, refraction is nothing but bending of light, right? When the light travels in a homogeneous medium, it always travels in a straight line. Or you can say, when the light travels in a same material, it always travels in a straight line. But what happens when the light ray travels from one medium into another medium? They bend, their velocity changes. Why? Because the different medium has different refractive index. Okay, so I'll explain you with the help of diagram. So this is refraction of light. Okay, so refraction of light, suppose. Okay, so this is interface. Suppose this is air medium, and suppose this is water. This is water medium. Water medium. So we can take different medium also. You can take glass, water, or air, glass, whatever. But here we are assuming air and water. So air medium is first medium, and say this is second medium. Now you see this line I have drawn here. This line distinguishes between the air medium and water medium. So this is what we can call, this is interface. This is interface between two medium. I hope it's clear. Okay, so let us consider a ray of light travel along AO. Okay, it encounters this interface, means it strikes this interface. So since this interface is transparent, so this is a normal at the point of incidence. Okay, so once this ray of light encounters this medium, it travels or it enters to the another medium. So this is enters to the another medium. So this phenomenon is called refraction of light. So what is refraction of light? So refraction of light can be defined as when the direction of propagation, right? When the direction of propagation of an obliquely incident ray of light that enters the other medium changes its direction at the interface between two media, then this phenomenon is called refraction of light. So I use the word obliquely. Obliquely means the angle of incidence. Angle of incidence may be greater than 0, but it's always less than 90 degree. So we can say the angle of incidence will lie between 0 to 90 degree when I mention the word obliquely. Okay, I hope you got this. Okay, so here this is this is O is point of incidence, so this is N is the normal, so this is N and dash. So this is angle of incidence and this is angle of refraction. Is it clear? Okay, there are two laws of refraction as you already got in your lower class. The first law of refraction is, as you can see, the incident ray, refracted ray, and normal at the point of incidence on the interface, they always lie on the same plane. Okay. So next one, the next one is the sign of angle of incidence, means the ratio of sign of angle of incidence to the sign of angle of refraction. This is R. It looks like gamma, but this is R. So this R. Okay. So what is second law of refraction? The ratio of sign of angle of incidence to the sign of angle of refraction is always constant, and that constant we can represent it by n to 1. I'll tell you what is n to 1. So this ratio is always constant. So you have to remember the law of refraction is experimentally given by the Snell. So this particular expression is also known as the Snell's law. Okay. So n to 1, what is n to 1? N to 1 is known as refractive index. So refractive index of which medium? The refractive index of medium 2 with respect to medium 1. There is a meaning why I am writing this n to 1. This represents refractive index of medium 2 with respect to medium 1. Why? Because the ray of light is traveling from medium 1 to medium 2. I hope it's clear? Okay. So now again, this ratio can be expressed in different way also. Okay. Now you see, suppose the velocity of the light in this medium 1 be v1. As you can see, when it enters another medium, it changes the direction. Since the velocity is a vector quantity, once there is change in direction, there is change in velocity, right? So suppose this velocity is v2. Okay. So this v1 and v2, maybe in some cases v1 is greater than v2, and in maybe some other cases v2 might be greater than v1. This depends on the medium through which the light is traveling. So here we can write like this also. So sine I divided by sine R equal to, so first medium, this is velocity v1 and this is v2. Okay. So this is the ratio of these two velocities, right? Ratio of the velocities of two medium. So this refractive index, so we can equate to the refractive index. This is known as relative refractive index. This is known as what? Relative refractive index. When I say relative refractive index, it means that there may be glass water medium, right? But there are two types of refractive index. One is relative refractive index, and in some other book you'll get the absolute refractive index. When I say absolute refractive index, it means that one medium must be air medium and another different medium. It may be glass, it may be water, but one medium must be, or permanently, that should be air medium. So when one medium is air medium, then that refractive index we can term as the absolute refractive index. As we usually denote the speed of the light in air medium by c. So for the absolute refractive index, we can write c divided by v, where c is the velocity of the light in air and v is the velocity of the light in any medium. So this is about the refraction and its laws. And now you come to know what is refractive index, right? And you have to remember refractive index determines the characteristics of the medium, right? So refractive index determines the characteristics of the medium, and it is independent of angle of incidence. Refractive index is independent of angle of incidence, but it depends on the wavelength. Okay? And you have to remember one thing. When the light undergoes refraction, right? When the light undergoes refraction, there is no change in frequency. What? There is no change in frequency. That's why when the ray of the light travels from one medium into another, there is no change in light. Where there is no change in frequency, there is no change in light. I hope it's clear now? Okay. So here again, now we'll discuss some elementary results based on the refraction of the light. So one, it's given in our book. This is lateral shift. Another one is real depth and apparent depth. Okay, first let me tell you what is lateral shift. So this now we are going to discuss the elementary results based on the refraction of the light. The first one is lateral shift. Lateral shift. Shift, as you can know, this is displacement. So let us consider a rectangular slab. It may be, as for example, say this is glass slab. Okay. So here the point of incidence, I'm drawing normal at the point of incidence. So this is the ray of light. Okay, this is the ray of light strikes on this particular point O. So O is the point of incidence and I must be the angle of incidence. So it will, when the ray of light encounters the transparent medium, it will suffer refraction, say like this. Okay, and again this is another interface. Say let me draw a normal. So this is normal. Okay. So here the ray of light suffers 2 times refraction, right? In this interface, this is, we can say, air glass interface if we consider the glass slab, and this one is glass air interface. Okay, so this is called incident ray and this is called emergent ray. As according to geometry, since these 2 rays are parallel, so this angle must be I. So generally, since this is emergent ray, so we can call this angle of emergent, but I is always equal to E because these 2 rays are parallel. Okay, why I'm drawing this one? Okay, so because this is the actual direction of the ray of light. If we would not have been placed this glass slab, the ray of light was supposed to travel in this direction. But because of this glass slab, the ray of light shifts or displaces its path and it emerging out in this particular direction. Okay, so what is lateral shift? What is shift? There is a difference between the shift and deviation. Shift and deviation. Okay, in this particular case, the light is suffering lateral shift. When we say deviation, there is change in direction. When we say deviation, there is change in direction. Okay, you see here. Okay, now if we see the direction of this incident ray and this emergent ray, this is traveling along the same direction, so there is no deviation, there is lateral shift. But how much distance it displaced from its original path? So how we can calculate? Because as we can see, these 2 lines or these 2 rays of light are parallel to each other. There is a simplest method how we can find the distance between these 2 parallel lines. You just draw a normal. You will get the distance between 2 parallel rays. Okay, from this point I'm drawing a normal. So here says this distance is D. This distance is the lateral shift. So if we have to define what is lateral shift, so we can say that the perpendicular distance between the emergent ray and the direction of the incident ray, that particular distance is called lateral shift. I hope it's clear now. Okay, so in board exam, derivation is not that important, because most of the time they never ask the derivation, but some short question might ask from this particular part. They might ask you when the lateral shift is maximum. When the lateral shift is maximum? When angle of incidence is equal to 90 degree. Okay, so now lateral shift depends on the thickness of the glass slab or thickness of the rectangular slab. If we increase, so this is the thickness, say T. If we increase the thickness of the glass slab, then the lateral shift will increase. And next point is, if we increase the refractive index of this particular rectangular slab, then also the lateral shift will increase. And if we increase the angle of incidence, then also the lateral shift will increases. I hope it's clear now. Okay, so next topic is real depth and apparent depth. So for this one, so this is a, you can say this is tank. Okay, so say this is water tank. Okay, this is water tank, this is the bottom. So suppose I am placing a coin. I'm placing a coin on the bottom of the tank. What if I fill up this water tank with the liquid? Say this liquid is water. Okay, so now, so this is a coin placing at the bottom of the tank. Once we fill up this tank with the water, okay, the position of this particular coin will changes. So it will raise. So let me explain with the help of refraction of the light. Okay, so this is the interface. So I'm drawing a thick line here. This is the refraction. This is the interface. Okay, so suppose this is a ray of light emerging from the coin, and here in this particular interface it will suffer what? Refraction. Why? Because this is water medium and this is air medium. Okay, suppose, okay. Let us consider one more ray because we have to form the image. Minimum we need 2 rays. Suppose this is another ray. Okay, so I'm not using scale, so it's not that straight, but just you try to adjust with this one. Okay, now it's clear. So these are the 2 rays suffering refraction. These 2 rays are emerging out from the coin. So when we extend back these 2 rays, okay, here is the image formation point. So this is the actual position of the coin, but when you see this coin, okay, you will see the position of the coin in this particular position. So there is this position is called apparent position. Apparent position. And this was the real position. Real position. So why this phenomenon is happening? Only because of the refraction of the light. Okay. So from this phenomenon, we have sometimes the numerical question might ask. So this is one relation. This is real depth divided by apparent depth. Okay, here H1 I am taking this real depth. What is the real depth? This is the real depth. Real depth. This is H1. From this coin to this, okay, this represents the real depth, and this position from this image to this point, this will represent the apparent position, and say this is depth to be H2. So it is given by mu equal to H1 by H2, real depth by apparent depth. So this relation is important. Why? Because in exercise there is a numerical. We can solve the numerical by using this relation. Okay. So now next we'll discuss the principle of reversibility. Principle of reversibility. Okay. Principle of reversibility. So sometimes in exam the question might be like this: prove that refractive index of medium 2 with respect to medium 1 is reciprocal of refractive index of medium 1 with respect to medium 2. Okay. So I'll explain this with the diagram. Say this is air medium. Say this is medium 1. Say this is water medium. So this is water, and say this is medium 2, and this is air-water interface. Okay, so this is normal at the interface. Suppose the ray of light incident in this incident obliquely. So once it incident on the interface, it will suffer refraction like this. Okay. So what we are doing? Let us place a plane mirror under the water. Like this. So this is a plane mirror. This is a plane mirror. Okay. And this refracted ray strikes the plane mirror at an angle equal to 90 degree. And you have to remember one thing. Suppose this is a plane mirror. This is a plane mirror. Suppose ray of the light is incident on this plane mirror perpendicularly. So after reflection, it will retraces the same path. So when the ray of light incident on any surface at the direction or in the perpendicular, so after reflection they will retraces the same path. They will bounces back into the same path. And in case of the refraction, suppose this is the interface. Suppose the ray of light is incident normally. So after refraction, it will passes through the same path. Okay, now. Okay, so again, so at this particular point, refraction takes place, but here, because this is a plane mirror, so here the reflection will take place. So since this ray striking the mirror perpendicularly, so after reflection, it will retraces the same path. And here, again, it will suffer refraction, and after refraction, it will travel back to the same path. Okay, so this is principle of reversibility. So now once I write the statement, you'll get to know what is principle of reversibility. Okay. So principle of reversibility states that if a ray of light after suffering any number of refraction and reflection has its final path reversed, it will travel back along the same path. Okay. So if a ray of light after suffering any number of reflection and refraction has its final path reversed. See, here the refraction and reflection, and here at this particular point we are reversing the path of the light, and after once we reverse the path of the light, it will retraces the same path. Okay, this is the statement of the principle of reversibility. Now we will try to understand this analytically. Okay, so this is medium 1 and medium 2. So in the first case, say I am writing this is case 1. Okay, so in the case 1, the ray of the light is traveling from medium 1 to medium 2. So in the first case, the ray of light is traveling from what? Medium 1 to medium 2. So therefore, the refractive index of medium 2 with respect to medium 1. So we can write N21, refractive index of medium 2 with respect to medium 1. Okay. Now we'll use the Snell's law. Suppose this angle is I, because this is angle of incidence, and say this angle is R. This is angle of refraction. So we can write sin I by sin R equal to 1. Okay. Now in the second case, say this is case 2. In the second case, the ray of the light is, see, the ray of the light now striking the plane mirror, and it is traveling from medium 2 to medium 1. So in the second case, what's happening? The ray of the light is traveling from medium 2 to medium 1. So we can write the refractive index of medium 1 with respect to medium 2. Why? Because the ray of the light is traveling from medium 2 to medium 1. So I'll write like this, refractive index of medium 1 with respect to medium 2. Okay. Now, according to Snell's law, sign of angle of incidence, right? Sign of angle of incidence. But in the second case, what is the angle of incidence? This is R, because the ray of the light is traveling from this medium to that medium. So here the angle of incidence is R. And what is the angle of refraction? This is I. Okay, so this is equation number 2. So now multiplying equation number 1 by equation number 2. So I'll write here. So now 1 multiplied by 2, or you can write multiplying equation 1 by equation 2. Okay. So here equation 1, this is N21 and this is N12 equal, we can write sin I by sin R into sin R by sin I. Okay. So left side I have multiply, and with the right side term I am multiplying. So here like terms, sin R will cancel out, and sin I will cancel out. So here we will get 1. So 2 1 into 1 2. So we can write N 2 1, so N 1 2. Okay. So this is the final expression now we have derived. Okay. So from the principle of reversibility, we can come to the very interesting conclusion that the refractive index of medium 2 with respect to medium 1 is reciprocal of refractive index of medium 1 with respect to medium 2. So this is about the principle of reversibility. Okay, now we'll discuss a very small topic. This is refraction through multiple medium. So we can take so many medium, but here for the simplicity, I'll take only 3 layers. Okay, suppose this is air medium, say this is water, and say this is glass. Okay, this is combination of water and glass. Okay, this is the compound medium constituting water and glass medium. Okay, so this is air medium and this is also air medium. Okay, so this is medium 1, medium 2, and this is medium 3, again this is medium 1. Okay, so this is normal to the interface, and say this is incident ray. So once it incident on this particular interface, it will suffer refraction. So this is again here, it will suffer refraction, okay, and it will emerges out in this way. Whenever you draw the diagram, ray diagram, you have to make sure that this emergent ray must be parallel to the direction of the incident ray. Okay, so say this is angle of incidence I, and this must be angle of refraction, so this is R1. So if this angle is R1, this angle must be R1. So this angle is R2. I am writing outside because space is quite less. So this is R2. So if this angle is R2, this angle must be R2. Okay, and this angle is E. Okay, because this is angle of emergence. But as I told you, this angle of emergence is always equal to the angle of incidence. Why? Because these two rays are parallel. Okay. Now, for the first interface, okay, for the first interface, if I write for the first interface, suppose first case, okay, I'll write case 1, or we can write like this: A, B, C, D, and here suppose E and F. Okay. So for the interface AB, okay, for the interface what? AB. For the interface AB, okay. So what we can write? Refractive index of medium 2 with respect to medium 1. So here sin I divided by sin R1, say equation number 2. Sorry, equation number 1, sorry. And for the interface, say CD, for the interface CD, so we can write, see, this is medium, for the interface CD, this is medium 2 and this is medium 3. So we can write refractive index of medium 3 with respect to medium 2 is sin, we can write R2 divided by, sorry, this is angle of incidence R1 divided by sin R2. Say this is equation number 2. Okay. And for the last interface, so this is interface EF, right? Interface EF. Interface EF is the interface between 3 and 1. So here we can write, so ray of the light is traveling from medium 3 to medium 1, so we can write refractive index of medium 1, right? Refractive index of medium 1 with respect to medium 3. So sin, what is angle of incidence? This is R2, and angle of reflection is sin I. Okay, so this is equation number 3. Okay, so if we multiply all the results here, okay, so if we multiply all these 3 equations, now you see, so n21 multiplied by n32 into n13. Okay, so okay, I am writing here sin I. So let's write here sin I divided by sin R1, sin R1 divided by sin R2 into sin R2 divided by sin I. Okay, now sin R1 is cancel out, sin I cancel out, sin R2 cancel out. So this is 1. So we can write n21 into n32, n13 equal to 1. Okay, from this relation we can write n32, we can transfer all the equation to the other side. So this will become n21 into n31. Okay. So this is the relation. This is a very important relation. Why I am teaching this one? Because this relation is in our textbook. Okay, so class is over, dear students. Okay, so almost we have covered this refraction part. So today we have discussed what is refraction, what are the laws of refraction, and some elementary result. This is lateral shift and real depth and apparent depth, and this is principle of reversibility, and this is refraction through the multiple medium. So this is about the refraction of the light. In next class we'll discuss what is total internal reflection, what is internal reflection, and what is critical angle, and some applications of the total internal reflection in nature as well as in the technology. So bye dear students, study well.